uniformly rotating frame, uniformly rotating frame, uniformly rotating frame, coriolis force, uniformly rotating frame, that means coriolis force. This is the x-axis, this is the y-axis, this is the y-axis, this is the x-axis, and this is the z-axis. This is the z-axis, and this is the origin point O. Let us consider a reference frame S dash. Let us consider reference frame S dash, S dash, S dash, Y dash, shown S1, S dash, rotating with a uniformly angular velocity omega, rotating with a uniformly velocity omega, rotating with a uniformly velocity omega x dash, and this is the z dash, uniformly velocity omega with respect to an inertial frame S, with respect to an inertial frame S, S dash reference frame rotating with a uniformly angular velocity omega with respect to an inertial frame S. Then circular velocity equal to omega t. Then let us assume both frame S and S dash have a common origin O. Suppose now we have a moving particle P. Suppose we have a moving particle P. Suppose we have a moving particle P. Like a fly or an ant walking on a rotating piece of cardboard. The value of its position vector r at any instant t will obviously be the same in either frame of reference, although its components will be different along the three axes. If the particle be at rest with respect to the inertial frame S, it would appear to be moving with relative linear velocity minus omega into r in the non-inertial rotating frame S dash. Frame S dash, linear velocity. Therefore, if its linear velocity in frame S, if its linear velocity in frame S V, vector V equal to vector dr upon dt. It will appear in frame S dash to be, it will appear in frame S dash to be vector VR dash equal to vector dr upon dt minus vector omega cross vector r. So vector dr upon dt h dash, vector dr upon dt h dash equal to vector dr upon dt as minus omega vector cross vector r. So v dash vector equal to vector v minus vector omega cross vector r, cross vector r, cross vector r. So vector dr upon dt into s equal to dr upon dt s dash plus vector omega cross vector r. So vector v equal to vector v dash plus omega cross vector r. The above, this is the equation number 1. This is the equation number 1. The above relation first relates the rate of change of a vector r in this case, the rate of change of vector r in this case in two given frames of reference s and s dash, and hold good for other similar vector and may be expressed as an operator equation. D upon dt as equal to d upon dt s dash into plus omega vector cross. Applying this to the velocity vector v in order to reduce the relationship between acceleration of the particle in two frames of reference. D vector v upon dt is equal to d vector v upon dt s dash plus omega vector cross vector v. Substituting the value of b, we have substituting the value of vector v, we have vector dv upon dt as equal to d upon dt vector v r v dash plus omega vector cross vector r s dash plus omega cross vector v dash plus omega cross vector r. So d vector v upon dt equal to dv dash vector upon dt plus d omega vector upon dt cross vector r plus omega cross dr upon dt s dash plus omega vector cross vector v dash plus omega cross vector r. Now d vector v upon dt is the acceleration of the particle, is the acceleration of the particle, as observed in the inertial frame S, as observed in the inertial frame S. Let us denote it by a and denoting dv by dt in the rotating frame s dash by a. If let us d vector v upon dt equal to a and d vector v dash upon dt equal to a dash, then we have vector a equal to vector a dash plus 2 omega cross vector v dash plus d omega by dt cross vector r plus omega vector cross r. Equation number 2. So dr upon dt vector s dash equal to v dash vector. Since the angular velocity omega, one minute, please 1 minute. Since the angular velocity omega is uniformly, angular velocity omega is uniform, then d omega vector upon dt equal to 0. So vector a equal to vector a dash plus 2 omega plus vector v dash plus omega cross vector r. Hence, here 2 omega cross vector v dash is called coriolis acceleration. This is the cross vector. It's called coriolis acceleration after coriolis acceleration after the name of its discoverer. After the name of its discoverer. The term appears only when the particle moves in a rotating frame. The terms appears only when the particle moves in a rotating frame. So vector v dash equal to not equal to 0. The terms omega vector cross vector r is a centripetal acceleration. Centripetal acceleration. Centripetal acceleration. Acceleration in the inertial frame. Acceleration in the inertial frame. Acceleration in the inertial frame equal to acceleration observed in rotating frame. Acceleration observed in rotating frame rotating frame plus coriolis acceleration coriolis acceleration plus centripetal acceleration centripetal acceleration centripetal acceleration acceleration in the inertial frame is equal to acceleration observed in rotating frame plus coriolis acceleration plus centripetal acceleration. Okay, thank you.